Before I move into the next one, I want to take a look at the question, and then I'm going to jump over to a different image. Number 5 says rank the following in order of increasing energy, and then we're given several different values here. And the first thing to remember is that principal quantum number, those very first numbers listed there, are usually what tell us the amount of energy that it has. However, in chemistry, we understand that there are exceptions and different things can happen. And this is an image that we'll be using for the rest of the semester and quite a bit today and tomorrow. And this is showing you those different sublevels and showing you those principal quantum numbers and how they increase in energy. So if you look at this top image, okay, and we look at the values right here, we see that this, as we increase, the energy increases. So for example, 1s has less energy than 2s. 2p has more energy than 2s. 3s has more energy than 2p. And right here, notice the difference. Most of you would say, oh, that's a principal quantum number of 4. It has more energy. But that 3p sublevel actually, just a tiny bit before the 4s, notice right here that 3d, see that it's actually above the 4s. So that's why you've got to be really careful when you look at those principal quantum numbers. This is a chart, a diagram that you will always be given if you're asked a question like this. You do not need to memorize what order they go in. I will show you some tricks on the periodic table so you can figure it out. But now let's try to answer this question given the information below. It says rank the following orbitals in terms of increasing atomic energy. Well, right off the bat, we see that this 1s is definitely the lowest. So we are going to list it first. I'm going to cross it out, make sure we've used it. Then we see 2s, 2p. Well, right here's a 2s. It's next, and then the 2p is after that. Okay. After the 2p, we jump to the 3s and then the 3p. There's that 3s, and then there's the 3p. Next would be 4s, and then 3d. And again, that's where students a lot of times will get confused. It is not something that you need to memorize. I'm going to show you how to use the periodic table to figure that out. What you're looking at here is what we'll use in a minute to take a look at orbital notation. And it's a way, again, for us to show where those electrons are placed within these sublevels and within these orbitals. Okay. So coming back over here, practice with quantum numbers. It says how many orbitals in an atom can have the following quantum number or designation? 3p. What does that look like? That is energy level 3, and we understand that p has 3 orbitals on it. So how many orbitals in an atom can have that quantum number designation? 2, 4, and 6. Okay, that's what the 3p would look like. 4p, 2, 4, 6. 4px actually means something a little bit different. So here's that same 4p, but what that is saying is that right there is talking about one specific orbital. There is only one orbital that can have that 4px designation or quantum number set. 6d would have 5 orbitals, 1, 2, 3, 4, and 5. 5d would also have 5, 1, 2, 3, 4, and 5. 5f would have 7 orbitals, 1, 2, 3, 4, 5, 6, and 7. And 7s, again, that s always only has 1 orbital. So even though we see that 7 and you think, oh wow, that's a really high energy level, it is a high energy level, but it still only has 1 orbital. The n equals 5 is a tiny bit tricky because we can't go that high. So we're going to kind of leave that alone. We're going to save that one for Chem 2 and not even go there yet. These bottom questions are pretty straightforward. The quantum number n describes the energy of an atomic orbital. The shape of an atomic orbital, so remember shape is that SPDF, is given by the quantum number L. You could also call that angular momentum, but L is good for us. The maximum number of orbitals that may be associated with the set of quantum numbers n equals 4 and L equals 3. So let's think about that. What does L equals 3 mean? That means 4F. And understand that F has 1, 2, 3, 4, 5, 6, 7 orbitals. So the maximum number of orbitals you could end up with would be 7 orbitals. The maximum number of orbitals that may be associated with this, and notice here we're getting a little bit more specific. So I see that energy level of 3, L is 2. And since L is 2, come back up here, think about what 2 means. That means D. So we're talking about 3D, which means 1, 2, 3, 4, 5. Now you see this, and this is something we haven't gotten to do a lot of practice with, but it's that M of L, and it's telling us that we're looking at the -2 orbital. Remember what we said earlier? We said we can actually give these orbitals numerical values, and that's what I'm going to do right now. -2, -1, 0, +1, +2. And since it's talking about the -2 orbital, I know that it's talking specifically about that orbital right there. So the maximum number of orbitals that can only exist would be 1 orbital right there. When n equals 5, the possible values of L are 0, 1, 2, 3. You've got the S, you've got P, you've got D, and you've got F. And the maximum number of orbitals that can be assigned to the n equals 4 shell, you could have 4s, 4p, 4d, and 4f. We understand that that has 1 orbital. 4p has 1, 2, 3. 4d has 5 orbitals, 1, 2, 3, 4, 5. And 4f has 7. 1, 2, 3, 4, 5, 6, 7. So 7 orbitals plus 5 orbitals plus 3 orbitals plus 1 orbital is a total of 16. Okay? And again, we've already talked about these answers in class. I just wanted you to be able to hear them and kind of see that work one more time.